Okay. Okay, that's better. So. Yeah, next time it falls off, I'll wrap it over my neck. Yeah, so good. So let's make it this thing. Oh, yeah. The slideshow. Okay, good. Yeah, so what I want to talk about is a new topic. I mean, that they haven't talked about before. Actually, something that now working on. But maybe, I mean, before switching to that, I mean, someone mentioned that last time we, didn't talk about future, about what, talked about all the experiments that are happening. I mean, varying quality that try to see the even odd effect, try to see the odd parity extensions and so forth. But maybe it's interesting to discuss what the future of that is. And let me still. Mm-hmm. Yeah, so what we talked about, lecture 1, lecture 2, were thermographic electron fluids, where collisions are, because of two-dimensional Fermi surface phase space constraints, collisions are collinear, namely particles collide at all angles, ones which relax angles and allow particles to randomize their state are the ones which are head-on. And so that leads to many interesting things, leads to long-lived excitations that have very long lifetimes, and all these, anomalous hydrodynamics, the exotic scale-dependent viscosity, and all these things that we discussed. Interesting to put a list of questions that maybe good to pose for the future. So maybe question number one is other examples of collinear tomographic behavior. Obviously, there are many two-dimensional systems where Fermi surfaces are circular or near circular. I mean, various graphene multi-layer systems are of that kind. But also, I mean, you can look a bit beyond graphene universe. And let's say if you take cold gases, I mean, there are cold gases, Fermi gases, in which collisions are dominated by Feshbach resonances between fermions, and then Feshbach resonance looks like you have a pair of fermions that comes together and becomes a bound state, and then a bound state Feshbach boson can have a long lifetime and then decay again into fermions. And so this process, I mean, kind of singles out the processes in which particles collide head-on and then go away head-out. I mean, and so in these systems, I think one may find examples of a tomographic behavior related to what we discussed. So this will be a 3D rather than 2D. So different, but otherwise maybe as interesting as that, right? So that's thing number one. Then thing number two are that these long-time memory effects that we discussed. I mean, they are assisted by collisions, and so they will not happen at very cold temperatures. They require finite temperature. So in this regime where we have long-lived extinctions, we benefit from warm temperature being non-zero and Fermi liquids being warm. And so what we see that warm Fermi liquids are more rich, extinctions in them are more rich than the ones in cold Fermi liquids, because cold Fermi liquids, there are everything we know about Fermi liquids that stays there when you and it's 2D and it goes in that collinear tomographic phase, then you get more interesting and more interesting behavior there, right? And so, I mean, when you have these long-lived extinctions, I mean, one can think of many interesting phenomena that exploit this long-time memory. I mean, you can take an extinction that normally would be short lifetime and then somehow store it in the odd parity, in one of these odd parity harmonics, and then read it out later. And then in that case, you will, there will be long-time memory. These long-time memory effects will be put to a good use for information storage or something similar. It hasn't been worked out yet, but clearly there is an opportunity. And then lastly, yeah, there are nonlinear effects. I mean, as we all know, any degrees of freedom that are long-lived are prone to strong nonlinearity, because if you pump it, it stays in that state for a long time, and then nonlinearities become stronger, and so there should be, don't know yet, but expect that there will be some nonlinear effects which are enabled by this tomographic regime. Again, you need to warm up to reasonably warm temperature where electron-electron collisions are already doing something interesting, and phonons are not yet doing it. So actually below Blok-Green-Eisen temperature, but there is a room for that, and graphene and gallium arsenide and various other systems where this is studied. And yeah, lastly, I mean, someone asked this question last time, but I think maybe just put it on the list again. I mean, what about turbulence? I mean, many people ask what will electron turbulence will look like, and there are probably many scenarios, but one scenario is because if we're in that collinear, in the tomographic regime, one can try to benefit from these long-lived modes and excite them, and if they're excited, then they can be excited and long-lived, and then they'll talk to each other, have a long time to talk to each other, and then there'll be a non-trivial, non-linear behavior which is long-lasting and can be externally controlled. And so that's maybe one route to turbulence in two-dimensional Fermi gases, which is enabled by these demographic effects. So I think this is kind of all I have to say on that. But I'm sure there are other things that can be added, and happy to answer any questions. Yeah, sorry.
I'd like to ask about the turbulence. When you say like for 2D electronic turbulence comparing to other kinds of 2D turbulence, what are the main common features and what are the main differences?
So no one has seen anything like turbulence in electron fluids, as far as I'm concerned. I mean, there were experiments claiming that, but at Harvard, but that later turned out to be just dominated by hot phonon effects. So I don't think there are any on the experimental side. There is nothing, not much to discuss. On the theory side, I mean, people tried just, in early days of graphene, people tried the ideas of if we can mimic Navier-Stokes equation on graphene, then we can do everything, all the good things we have from the Navier-Stokes equation, including turbulence, we can, mimic that on graphene. And there are theory papers that exploit this and show that you can get to reasonably high Reynolds numbers, but hasn't been verified yet. Yeah.
I was just wondering about the nonlinear effects.
Yeah.
So, setting turbulence aside, kind of a more under control examples of this is these long time tails coming from, in low dimensional Navier-Stokes, noisy Burger's equation.
Mm-hmm.
And those all come from, truly qualitatively new effects come from convective nonlinearities. And so, so I'm wondering whether here, is there some new quantitative effects, or there's something you expect there's some new qualitative effects?
Convective nonlinearities, you mean like Mazenko, Andreev, that kind of stuff?
No, just the convective, V grad V kind of terms. Just in the Burger's equation you have.
In 2D or in?
Let's say in 2D.
In 2D, yeah.
So those nonlinears are relevant in the presence of noise. But so do you mean?
I mean, so yeah, so that sounds actually, okay, so verbally, I don't know what precisely you mean, but verbally it sounds somewhat similar to what we thought about in connection to this stuff. So you can try to understand the long-time memory effects in the following way, because we understand that this is related with odd parity modulation of the Fermi surface. One can construct a reduced picture where you take Fermi surface shape and project out even parity harmonics, and then write some effective low energy field theory for odd parity harmonics. So treat shapes in K-space like liquid crystal membrane or something like that.
Like some hydrodynamic theory for velocity or something.
Yeah. So we, nothing published, but we tried that, and it sounds kind of similar to what you're describing. So maybe we should talk.
Okay.
Yeah. Any questions? Yeah. So maybe also opportunity to answer the question that you asked last time, which I didn't have a good answer for. So there was a question about a qualitative explanation for this increased conductivity, how you switch from T square to T linear T, and can one understand that? Also, is there simple explanation for fractional power locate to the 5/3? And so on the second question, I don't think we have to say much. I mean, we did many calculations, different level of different kind of calculations, some mean field, some exact with continuous fractions that I described, and they all eventually give 5/3. But so we're pretty convinced that that's a correct result. We don't have a simple explanation. Would be very nice to have that, like Kolmogorov derived 5/3 law from saying that all completely chaotic, but you have to think about constraints due to energy conservation and other conservation laws. So don't have that here. Maybe we will. But
much more detailed mathematics. That's why it's interesting. It's much more detailed mathematics from that.
Yeah, I mean, it probably would just lazy, because it's a much simpler problem than Kolmogorov. So there should be a way to answer that. But then, I mean, on the other part of this question, T dependence. So the T dependence, explain linear T dependence qualitatively. I think we know how to do that, because we can, what we can do, and we had a paper on that, which I didn't talk about. You can take, I mean, maybe I can show you this picture and kind of use it for that purpose. Yeah, so I mean, so we know that at lower temperatures these odd parity excitations become very long-lived, and we can ask to derive separate equations of motion for each odd parity harmonic, and in some approximation you can do it, and then you see that each of these harmonics becomes like its own degree of freedom, and it just these variables base some kind of Navier-Stokes equation, have diffusivity associated with them, and no, it's not on this paper, it's on the previous paper. Diffusivity associated with them, and then when you go to lower temperature, you have this regime when there is more and more of these approximately conserved quantities. I mean, they all have finite lifetime, but these lifetimes are very long, and so you have instead of one viscous mode, which is basically momentum diffusion that transports momentum. Here you get more and more of them lower temperature you go to, and so you kind of get a swarm at lower temperatures. You kind of get a swarm of these different degrees of freedom. Think of these odd-shape modulation of Fermi surfaces that are all doing it together and transporting current in parallel. And because of that, conductivity goes up and viscosity goes down, and that's the qualitative picture. And so then basically to understand how you go from T squared to linear T, you just need to estimate how many of these modes effectively help you to transport momentum at a different length scale. So for being able to do that, they need to be alive over that length scale. So their decay time should be small enough so that don't die down before they propagate through that length scale. And so that these are the constraints, and if you combine it all together, you do get a linear T dependence. And I think that is a reasonably good qualitative explanation for that. I mean, yeah. Okay. Any more questions? All right, good. So if not, then let me switch to this. All right, so this is a work unrelated to what we talked about before, but something related to electron fluids and somewhat related to electron fluids, and also a nice topic to talk about, and also happens to be of interest for me because that's what we're doing now. Turing instability in electron fluids, and so maybe start with reminding ourselves about what Turing instability is about. So basically, Turing, the great mathematician, became interested in later part of his life in the question of pattern formation in living organisms, and in particular how something like a zebra or gets its stripes, or leopard gets its spots, and so forth. And so so he had a a very general idea about how that might happen, and this is this has become important development in mathematical biology, and maybe more generally in applied mathematics, that we can talk about briefly and then see if there is any connection to physics. So with Turing, Turing kind of made an abstract construction formalizing what biologists tell us about how what happens when cells grow and grow organism and divide and make a tissue, how different chemicals diffuse through the tissue, and one can basically construct a general system of nonlinear equations of linearity and diffusion called reaction diffusion equation that explain those behavior and the way this is applicable to morphogenesis, that's the name for pattern information in biology, is described here. I mean, this is just to prove to you that I I read about it, but basically it is what I just said. I mean, there is a lot of terminology here, but basically the idea is there are some chemicals that control the growth of cells, and then they diffuse and they react with each other. And if you understand how they react with each other and diffuse, you can understand patterns. And more formally, this is done as follows. What people working on this write is some, let's say, minimal model that says we take two fields describing some relevant chemicals, and they obey diffusion equation and also nonlinear. There is also nonlinear interaction between them. And then assume that if you forget about diffusion, take k equals 0 limit, drop the gradient parts, then these two equations will be unstable. There will be a fixed point, but it will be unstable fixed point. And then if you let it go, then it will grow and blow up. But if you now turn on diffusion equation will tame the instability at large wave numbers. And so everything that happens at large wave numbers at short distances will be dominated by diffusion. And then at longer wavelength, longer distances, smaller wave numbers will be dominated by nonlinearity. And then out of that you get in a very general way to get pattern information. You can generate many patterns with stripes and spots and all other kinds. And so there is a whole business of applying it to a living world. So that's as much as I know about it. And happy to answer any questions. I mean, some people also go as far as to explain why in the same terms to explain why the human body has 5 extremities like head, hands, and feet, and why each of the extremities have 5 fingers and so forth, right? So you can take it pretty far, but I mean, that's a general framework that seems to be widely applicable. Happy to maybe stop and talk about anything of interest. Okay, then if not, we can just move on. Yeah. So the question that is interesting to me, and I don't think it has been studied much in that Turing instability literature, and there have been some papers, but not I think not as many as there should have been, is whether Turing instability can be triggered by current. And so if you have a system with flowing, and it develops some modulation. This modulation will flow together with current, and will look something like that. And space-time will look something like what you see in this picture. And so this is basically what I'm hoping to get in electron system, and that's where I'm heading. So one can first ask other examples of this happening, and so as a matter of fact, yes, there are examples of something very much like Turing instability in fluid layers, and that's known as roll waves. They're driven by Kapitsa instability, and it's a fun thing to read about, or even to see for yourself if you get a chance. But basically, the idea is the following. I mean, this is from a paper which is cited here in Fluid Mechanics Journal, but it's much older. I think the whole thing was discovered by Kapitsa in the year 1949 or something like that, and he wrote two papers. Kapitsa is the same guy who you know from Kapitsa pendulum. Take pendulum and vibrate, and the pendulum goes straight up. I mean, he also got Nobel Prize, but that's not important. But what people mostly know about Kapitsa is this thing, right? But he also did this experiment. He realized that if you take a fluid layer flowing down an incline, then it will develop a modulation like shown on this photograph, and so it's a long channel. This paper says channel is maybe 17 or 20 meters long, and so the flow starts from the inlet, which is somewhere where you can see it. But then, as it flows down, it breaks into these train of waves that you can see here if you look carefully. But this is also showing what sensors show. They had sensors at certain distances along the flow, a few meters apart. And this is how the modulation looks like on each of these sensors. So you see that each of the waves are roughly, equal distance from each other. I mean, not exactly, but they are roughly. They definitely have some periodicity, and they have certain characteristic shape, triangular in this case, more sharp on the front and more flat on the back. And this is just visually, this is similar to what Turing instability usually does. You get some pattern of stripes, and then this pattern of stripes is not necessarily. It's orderly, but not super like well periodic. If you think of your photo of leopard, I think this stopped working. But if you think of, yeah. So if you look at zebra, you see that it's kind of orderly, but it's not super well periodic. And so from that point of view, this is similar. Then if you want, what is this? Yeah. Yes, so there is this thing, and that's kind of what interests me. And what I want to do is pose the question: can we get something like that for electrons, so that electron flow develops an instability in which get a pattern generated? Now, the interesting thing about this kind of instability is that it happens and it leads to waves, but these waves are not self-sustained. They are not like what we're usually used to, like capillary waves or gravity waves on the surface of water. This is a laminar flow in which is very dissipative. I mean, the viscosity, thickness of the layer and the flow velocity is so high that it is dominated by viscous effect and not by the effects that usually drive waves. And so this is it's a wave, but it's a very different kind of waves. It happens in the viscous flow regime, and from that point of view, it is distinct from various various waves that we know much better. So there are these capillary waves and gravity waves, or in solids there are plasma waves or phonons, and all these waves they're self-sustained. I mean, basically, each wave mode is a harmonic oscillator. It got stiffness, it got inertia, and energy goes back between the two parts, and that's how the wave propagates. And it propagates with the characteristic dispersion, characteristic velocity, which you can derive from dispersion relation for these waves. Propagates with a group velocity shown here, and it exists at weak damping. I mean, all these waves shown here, they exist at weak damping. You need the damping to be much weaker than the frequency of the wave. So that's the condition for all these self-sustained waves to occur. In contrast, the roll waves, the Kapitsa waves sometimes called, they occur when the fluid is only when the fluid is moving, and they're absent in a still fluid, so they don't sustain themselves. And then they're excited. I mean, the interesting thing about it is that they're excited even when the flow is very dissipative. So the frequency of the wave can be much smaller than dissipation rate, like in that picture in the previous slide. And even despite that, they exist. They propagate with low velocity. Basically, they're carried by the flow, so their velocity is approximately equal to the velocity of the flow. So they do propagate, but they're not self-sustained. So these are the waves, roll waves. Or, yeah.
Relaxing.
Yeah, some relaxation. Yeah.
What are the boundary conditions that allow these waves?
So in this experiment, I mean, it's instructive to read this paper. So this is a channel that is, you can see how it's made. I mean, it's maybe 20 centimeters wide and 20 meters long. And a layer of liquid is thin, perhaps a centimeter, something like that.
It's connected to some reservoir.
Yeah, fluid is coming from some inlet.
Like at fixed pressure.
For viscous flow in such a long geometry, what happens at the inlet barely matters because it flows for a long time. It has time to adjust and relax. It's viscous. It's like flowing honey.
Yeah, but these instabilities, I mean, if I solve Navier-Stokes in some linear response, like it's very sensitive to the boundary conditions.
Yeah, not over long. I mean, imagine doing it yourself with honey. Then, I mean, it will, of course, what happens initially will be sensitive to boundary conditions and what you're doing, but then after a meter or 5 meters or 10 meters, it will stop caring about what happened initially. It goes into that steady state, which is we kind of see here.
Sorry, so is there some threshold velocity?
Yeah, threshold velocity or threshold incline. Yeah, so you see it. I mean, it's widely used these days in sculptures. I mean, if you go to a water sculpture, you find that artists quite frequently make use of it. They make a water flow down a vertical wall or inclined wall, and then it makes nice patterns that fun to watch. And I don't older you see it quite often. How much time we have? Just tell me.
45 minutes.
Okay, good. So maybe I can indulge in showing you experiment if it works here. Yeah, so you can also see them like on a unprepared on the road. So this is a place near where I live, where I go running. And so what you see here, I'm not sure if you can see here, but let me zoom on it. Yeah, what you see here what you see here is that the water coming from a pile of snow which is melting somewhere far away, and then what happens near the pile, I mean, the pile is not pulsing, obviously, it's just a pile of snow that has been there for maybe half a day. But then after water flows over 20 meters, it develops this, periodic modulation that you can see this quite clearly. Yeah. Yeah. Anyway, so that's as much as there is to say about that. Yeah. Any questions? Let me know. Happy. So what's interesting to discuss is an electronic version of that. If you take electron hydrodynamics or fermi-liquid hydrodynamics, basically what Luca talked about, and also many other people talked about, but I think he just talked about it yesterday. And if you take that, write down coupled equations for momentum transport and particle density transport, and there will be a continuity equation for particle density and continuum version of second Newton's law for momentum transport, where P is momentum density and big P is Fermi pressure. Fermi pressure needs to be taken for a moving Fermi system, and then gamma is indeed the momentum relaxation rate. Electric field is what drives it. So if you take that and then work out the details, I mean, happy to, I don't have slide for that, but we can do it on chalkboard if anyone is interested. Tell me if I should or shouldn't. Pretty simple. Basically, taking the same equations as Luca showed, but then taking a steady state flow, which is a solution here, and if you say that current and momentum density are not varying in space and not varying in time, so then you just balance these two terms against each other, electric field against dissipation, and then get a steady state flow. And then if you now test them with respect to instability, linear instability, then what you find is, maybe let me put a small picture on a chalkboard. Let me see what's there. Yeah, this is not very. Yeah. So if you think. Yeah. So first of all, go to first of all linearize and then Fourier transform. And then, plug it in these equations, do the same thing for momentum. Right. And then you get two coupled equations for delta n at k and omega, and then, and then you get then you get a linear problem, pretty much like in Turing's case. And then this linear problem, these equations for this linear problem will generate a dispersion relation telling you how omega is related to k. So you derive the dispersion relation. Dispersion relation, and then if there is instability, then in this dispersion relation, you get an increment. Maybe versus k will have imaginary part, and this imaginary part will be negative in a stable phase. And then you get a linear problem, pretty much like in Turing's case. And then if there is instability, then in this dispersion relation, you get an increment. Maybe versus k will have imaginary part, and this imaginary part will be negative in a stable phase. And then you get a linear problem, pretty much like in Turing's case. And then if there is instability, then in this dispersion relation, you get an increment. Maybe versus k will have imaginary part, and this imaginary part will be negative in a stable phase. positive in the unstable phase. And then, so then what you do here, take that plot, and then what you see for the yeah. Let's say if you're in a stable phase, your increment is negative, so you see dependence that looks like that, something like that, and then it goes to 0 at 0k because there is a particle continuity equation, and therefore the instability at small k, even if it happens over a very long time. And so because there is a conservation law, the increment always goes to 0 at small k. But away from small k, there will be some degree of damping, and so this will be damped. And then if you do it for the unstable phase, then we see a similar analysis. Do small k does something like, and so this is where growth happens. This is where growth happens. Also k at which is fastest is the wavelength which you expect to observe. So this is pretty. It's pretty similar in the case of Turing instability. Not the same though, because in Turing's case, these equations I showed, they don't have any. There are no conservation laws there. Because of that, when you do stability analysis, the transition from unstable to stable, from stable to unstable, happens a bit differently. So in Turing's case, what happens if you have an increment versus k, and it goes from unstable regime to stable regime, you typically see something like that. So in the stable regime, there is some dispersion describing damping of these waves, and then when you cross the stable unstable boundary, it does something like that. And then again, I mean, the k at which you see the fastest growing instability will be the wavelength that will determine the stripes of your zebra, how far apart are the stripes of your zebra. Yeah.
And what's the new ingredient? Because if you just do it for those equations under standard conditions, viscosity gives you, gives you damping, and so then you get just the white curve. So how do you get it?
Sure. Yeah. Let me talk maybe a bit more about what happens in Kapitsa's case, because this is well explained in Kapitsa's paper, and then we'll talk about this case as well. So Kapitsa actually wrote two papers on that. So he first wrote a theory paper. He solved Navier-Stokes equation for that flow, and presumably just he saw it on a sidewalk somewhere, and then decided that let's work out a theory. So he worked out a theory. So for Kapitsa's case, if you have a fluid flowing down so the theory paper gives the following argument. Then he did experimental paper that he where he also demonstrated them, but I mean, that one I haven't read that carefully. This one I read, and there is an error in it, but that doesn't change the essential conclusion. So here, if you take fluid flowing down an incline, then you can find a steady state flow, basically solving the hydrodynamics equation here. Gravity proportional to mg rho times sine theta the single, and it should be balanced against viscous forces. And viscous forces are, so there'll be a flow velocity pattern, parabolic flow velocity profile. Here they'll sketch like so, right? And then that will give that tries to stop it from sliding down, and will be proportional to viscosity times the length scale, 1 over length scale squared. So there will be this inverse square that's coming from the Laplacian and Navier-Stokes equation, right? So if you now times velocity, yeah, thank you, exactly, yeah, times velocity, yeah. So now if you solve the system equations, you find you see that velocity is proportional to the square of the fluid layer width, which means, I mean, which has a simple explanation. It just says that if your fluid layer becomes thick, then this friction becomes smaller, and then the fluid flows faster, right? So then he says, imagine that we allow my fluid to just do it different chalk, develop a modulation. So suppose it develops modulation, then it will flow faster. And then in these regions, it will flow slower. And then these regions will rush forward and will catch up with those more slowly flowing regions. And then, yeah, exactly. And then you will see a different color. Yeah, then at a later stage in time, you will see that develop something like that. Yeah, so you see the idea, right? So so that's indeed what you see. I mean, if you just look at the waves, plain obvious that this is indeed the right picture. And then, I mean, the technical details, I think, on the paper are not maybe so good. But then people later corrected it. I mean, there was a nice paper shortly after, maybe 10 years after, written by Andreev, the Andreev reflection guy, and so it actually did it very nicely and kind of sketched the same picture for the instability. And so here, I mean, if we want to apply this to graphene, then we need some analog of that sensitivity of flow to carrier density, and so that can come from different directions. But one property that we know, for instance, in graphene, various kinds of graphene bands, is that near band crossing, there is an increased particle hole scattering that Sabir and Andy others worked on. And so if your carrier scattering, if your carrier is tuned close to the Dirac point, there will be a strong sensitivity of that contribution to carrier relaxation rate on doping. And then from bar, the difference that electrons are 2D, this thing is 3D. It does the same thing. It makes the flow velocity very sensitive to doping in that region. And then, I mean, you can do essentially the same calculation that Kapitsa did, and I mean, modular various differences and see the instability. Yeah, I think I'm going to finish sooner, but then we'll have more time for lunch. Yeah. So anyway, so we did a calculation, and so if you do calculation, then you see. So this is actually what I did, and you see basically the same behavior as I sketched there, because I knew what I'm going to show you. But this indeed what comes from the analysis, and then maybe stop here and see if there are any questions. Yeah.
Maybe you can. I might have missed it, but what would the observable be in this electronic case? Because I think you're not going to see real time these waves.
Yeah, I mean, well, it depends on how fast they move. They're not moving super quickly. I mean, they're not plasmons. They're moving much slower.
Are they moving at the speed of sound?
At the current drift velocity.
Only at the current drift velocity.
That's right. Yeah.
Yeah.
I mean, which is high, but it's not. I mean, it's not anywhere as high as what people usually hoping to observe. And people observe plasmons, and plasmons are moving at 20th of the speed of light or something like that. So so this is much slower, so the frequency. I mean, we're not done yet, calculating it, so I can't tell you what frequency will be. It'll definitely be maybe 10 or 100 times lower than plasmonic frequencies, that's for sure. So there should be ways to observe. I mean, if people do it with plasmons, they should do it with that, not.
Are you saying just put a voltmeter and it will
even that might work, because if it's a gigahertz in a 100 gigahertz range, I mean, engineers could do that. But I mean, there are better ways. I mean, it's kind of like observing Bloch oscillations. Bloch oscillations is the same kind of problem. These are oscillations that you induce by current, but then the frequency oscillations is so fast that you don't know how to observe them directly. And so what people do with Bloch oscillations, they try to observe the reverse that there are Bloch oscillations. They irradiate the system by some external frequency with characteristic frequency, and they vary frequency and try to see a resonance of your external radiation frequency and the internal frequency of Bloch oscillation. Has never been seen. Bloch oscillations have not been observed in solids. That's one of the outstanding problems. That's what people are trying to do. They're trying to see the reverse Bloch oscillation effect.
Okay, I mean, I'll let you finish, but I'm just asking because I know in the context of this Diakonov assurance.
Oh, that's another interesting topic. We can get to that. But I mean,
but that's terahertz.
Yeah. So that's no different from Bloch oscillations. So that's also pretty hard to observe. So this will be much lower. Yeah. Well, this is one of the reasons I think it's interesting. Because Diakonov sure they excite plasmons. Plasmons means that you're bound by plasmon dispersion relation, and here it's yeah.
Yeah, for this instability, you need a free surface. Right? It's the instability of the free surface.
Yeah.
That's where.
Yeah. So the hope is that an electron system, instead of the height variable, there is a variable. So we're also writing like two-coupled equations, just like Kapitsa did. He reduced three-dimensional Navier-Stokes equation by integrating out this parabolic profile. He reduced it to two-dimensional system of two-coupled equations for density and flow velocity, and then studied instability there. But the first step was to integrate out the third dimension, which here we don't need to do. But then I think afterwards the analysis proceeds similar. Yeah.
Another question.
I have missed the point, but for the electron case, what's the relation between density and flow velocity? What, like, it's a physics I can see.
Yeah. So in the electron case, the flow velocity, I mean, will be related to current, like so. So you can get the same current by changing n and changing v, but allowing them to be related by this,
The higher density should lead to the higher or lower velocity?
constant current, high density, lower velocity.
The opposite of the Kapisa case?
No. Oh, okay. Yeah. Sure. Yeah. Right. But one need. Yeah. I agree. But I mean, there is instability nevertheless. I mean, all you need is to have it vary. But yeah, then okay. So then found instability. We're happy. But then I think the question is: does it occur? At what flow velocities does it occur? Does it occur at the flow velocities where you start exciting Diakonov-Schur things, you start exciting plasmons, or does it occur at much lower flow velocities? So maybe for those who don't know about Diakonov-Schur, maybe let me say a few words about it. So Diakonov-Schur, and if you haven't read this paper, I urge you to do it. So Diakonov-Schur wrote a beautiful 2 or 3 papers so their motivation was the same as everyone else's motivation, how to excite waves by driving current. They have taken an analogy with gas dynamics in musical instruments. So let's say if you have a musical instrument like a flute, you blow constant rate. Blowing into it at a constant rate, it starts to vibrate. So how they work? If you haven't seen it before, read of the dynamic example and electric problem. So the hydrodynamic equations for 2-dimensional electrons in a limit of 0 dissipation are identical to gas dynamics equations. And then after that, they say that why don't we just, treat it the same way as gas dynamics equations, and then step 2, work out the problem for gas dynamics equations, and then get instability out of it. I mean, if people want to hear the story, I can tell you more about it. But essentially, what they do is the following kind of argument: you have a channel in which you drive constant current, and then if you small amplitude plasmons propagating the channel, you propagate along the channel. Some boundary condition here, it opens up. Let's say it opens up here a different way, and Doppler shifted with lower frequency and lower velocity, and then they again, and so each excitation goes back and forth multiple times. And then the observation, if there is damping, then of course it will be damped. But if damping is low, and if there is an asymmetry between boundary conditions, which they carefully worked out, then there will be amplification effect for that going going back and forth. There will be a net amplification effect of the amplitude of that excitation, and then they say that if you are in that sweet spot regime, then you will see an instability. And so this explains why all these musical instruments are very asymmetrical, open on one end, and on the other end you do something with your fingers, I think that explains, at least cleared a lot in my mind. Yeah, so these are beautiful papers, and but from, I mean, if you forget about all these details, they excite. So in our language, they would excite a plasmon in this way, right? Yeah, so it will be in a terahertz frequency limit. But anyway, I'm not. So I don't think this is related to Diakon von Schur. I just talked about it because someone asked. But so here we are in a dissipative regime. So we're more like this Kapitsa wave flow. And
Sorry, so since you're talking about it, could you say again where the amplification comes from in that?
Yeah, it comes from the following interesting effect. So if you work out the Doppler shock propagating along the flow and fluid this way, and then being back reflected and propagating back, then we know from Doppler effect how the wave number change and frequency change, but also from the boundary conditions, we can work out how the amplitudes change. And you typically find that if it propagates this way with, let's say, this wavelength, and is back reflected, then when it will propagate back, the wavelength obviously will become shorter, but also the amplitude will grow bigger. So this amplitude will be smaller than that amplitude. So on reflection, under the conditions that the fluid is moving, you get a change in amplitude, right? And then, I mean, if boundary conditions are identical, then this wave packet coming here will back reflected, will change frequency and wave number by Doppler and will acquire this amplitude and that amplitude. But if boundary conditions are not the same, let's say one is semi-closed and the other is open, then you don't get a change. I mean, frequency and wave number change in the same way. They are mandated by Doppler shift, but amplitudes don't have to. So you get a different amplitude ratio from, let's say, open end and closed end. And then you can adjust parameters so that there is a net amplification. I mean, pretty neat, but that's what they say.
It's like fixed pressure on one end, and you hold the current.
Exactly. Yeah. Pretty hard to achieve in practice, but it's a nice paper to read to understand what happens on musical instruments, from my point of view. It's a clearest story about that. I mean, you can never find it more clearly explained. They had a couple of papers. They had a paper, maybe 3 papers that everyone should read. They had a paper in Journal of Applied Physics. I forgot, but there are, one should, like, if you haven't seen it, one should read it. Yeah, anyway, so coming to the end of it, I mean, so now that we see the instability, one can ask what's the phase diagram. And the phase diagram, one can vary flow velocity and vary the electron density, and then identify where it's stable, where it's unstable. So there are stable and unstable regimes, as you expect. Now the crucial question is, does the instability occur at fast flow or at slow flow? And so for that, what you want to do is to draw a relation that's this line where velocity, the flow velocity is equal to the Fermi velocity for a fixed density. So you can derive conditions. So this would be a parabola, and you put it on a graph together with the stability, and then compare, and then see that, well, at least over there, the instability occurs in the regime when Fermi velocity is much higher than your flow velocity. So you are in the slow flow regime, And so from that point of view, all these competing effects like potential Dyakonov Schur and or what's often considered, and I think, well, many people, including Andy, had papers on Doppler effect and stability when you induce a flow and then you have a plasmon on top of that flow. And if you Doppler shift plasmon frequency and increase flow speed to a high value, then plasmon frequency goes negative, and then it gets in the regime when it becomes beneficial to emit plasmon excitations, and then in other words, plasmon becomes spontaneously generated by current. But all of that happens. It's like Landau theory of critical velocity of helium, which predicts, very, very high velocity, much higher than observed in experiment, by the way. But anyway, so it's the same idea as critical velocity for Doppler shifted quasi-particles. And so here, all of that will predict high critical velocity, and pretty important to establish that we are far from that regime at slower flow rate, which seems to be the case here. Maybe the end of story, and let's see if there are any questions. When are we supposed to end? At half hour?
Yeah.
Yeah. Okay, so we can. Yeah, we can talk now. I mean,
Can you elaborate
ask something. Yeah.
elaborate on the electronic system you mentioned?
On what part of it?
I didn't quite understand the connection to graphene, I think you mentioned, or?
Well, okay, connection is on several levels. I mean, on one side, I think one can pose a general question, and it could have been done in 1949, but haven't been done. But now there are these instabilities that people see in graphene when they run high current through it. Oh, you haven't been in the first lecture. Yeah. So they see instability in graphene. There is a slide that I borrowed. Yeah. So there may or may not be a relation. But let me remind everyone what people see there. I'm not claiming anything definitive at this point, although that's the motivation. Maybe discussing the relation. They about this. Forget about Kapitsa stuff. So in this paper, what they have done is that there was a graphene sample in which they interrogated with current and observed that in the band they could apply fairly high current, and in the ohmic regime you could see the main Dirac point and the side Dirac point, and so it looked fairly conventional, shown here, right? But then if you increase, let's say, this is linear ohmic response as a function of carrier density, then you fix carrier density somewhere, let's say here, and then add this carrier density, study nonlinear IV. And then nonlinear IV is seriously nonlinear at ohmic here, but then all of a sudden becomes much steeper and then flattens out a bit. And then if you take dVDI, you see that in these regions there are spikes. So there are some singularities at some value of critical current. And that value of critical current, what was interesting in that paper, that value of critical current was very close, by order of magnitude definitely was close to the, so they could reach fairly high current value at which band population becomes, well, A becomes very asymmetrical, because if you have band with carriers in it and they're flowing at a drift velocity which is comparable with band velocity, then the Fermi distribution should be very skewed, right? But then more than that, I mean, they found that if they increase current, they can go to currents which are higher than that. If you take current and use this formula that we have here, and we usually know the density. If we know the density and know the current, then we can get drift velocity. Then over here, the drift velocity is higher than the band velocity. And that can only happen if there are carriers promoted from the conduction band to an upper band. And so beyond this instability point, there is a, that's what this paper says. I mean, I can tell you my contribution to that paper. That's this dashed line basically on that plot. But more important is that they found that they can produce inverted carrier distribution or excite carriers in a high band. And the remarkable thing is that this can be done reversibly. You don't burn your in an ordinary conductor, you never do such a thing because you will burn your sample. And here, because graphene is atomically thin and because around it there is some 3D material, nitride or something like that, you have good heat management here, and so you can play games with increasing current to very high values and then taking it down, and you can do it many times for hours, for weeks, for months, and nothing happens to it. So it's completely reversible. And then they could prove that this is indeed the story, that you see inverted carrier population. So you start populating band with opposite sign carriers, because if you let me first talk about this one. So in this picture you see this quantity, which is plotted here, dVdi, as a function of carrier current, as a function of current density. Current is along this axis, and then here it's carrier density. And so in each horizontal line will be like a blue curve here. And then so essentially these white regions are positions of these peaks as a function of tuning knobs. And so they do something interesting near Dirac points, but there's a pair of peaks that behave non-monotonically and show something interesting near Dirac point. So then, to prove that there are particles in holes, they applied magnetic field. And they had hole contacts on the side of their current path. They saw Hall effect changing sign when you go across that instability line. So you know that when you go across, your carrier main carrier type changes from particle to Hall and back, right? And so that's a proof that you have band inversion induced by current near these points. So then, I mean, then there are many details, but from point of view of what I was talking about, I think this paper can serve as a motivation. It tells you that we can go pretty high currents without anything bad happening system. So we can definitely be at the currents that, like what I talked about, and even much higher currents like those. And so this is a regime which is readily available, and we can predict that there will be instabilities like that seen in this regime, and so that's the relation. I mean, one can go further into that, but maybe that's a quick answer. Yeah.
If not, that's thank you again and break for lunch. The T-shirts are here. So we'll distribute them at the end of after the lecture.